So I just finished writing a little Python script, absolutely no error handling at all, that compares the ellipse perimeter approximation that I developed yesterday morning to one of Ramanujan's, which is extremely accurate, so it's a pretty good reference. But mine is much simpler. So yeah, here's the basic program. Let's run it. So it allows you to choose between eccentricity, which I am labeling here M, because I find the confusion between this and mass to be much less than the confusion between this and Euler's constant. So how about yeah. So you can choose between eccentricity and the ratio semi-minor axis over semi-major axis. If you set your semi-major axis to unity, then it's just semi-minor axis. So here, let's do, it doesn't matter, I'll do eccentricity. So it asks you to enter the eccentricity. Let's do, I don't know, 0.5. Now that gives us the basically if A is unity, that gives us the semi-minor axis. So the semi-minor axis is this if the semi-major axis is 1. And we can verify that this works by running it again. So okay, so here, this is the approximation that my formula yields. This is the approximation from one of Ramanujan's, this one. He produced several. They're similarly accurate, but they're slightly different from each other, like out in this kind of territory, out in 7 or 8 digits or something. But yeah, you can see that this by no means perfect, but it's like 0.1% off. Like that's pretty good. That's pretty good. Okay, so now let's try putting in the semi-minor axis, and I'm gonna put in this number here. So 0.8602540378444386. So if I did everything right, this should give back an eccentricity of 0.5. And it pretty much does. So there you can see these numbers are the same. Yeah, these ones are all exactly the same. This is the little rounding error is, yeah, that's just out at the edge of what Python's floating point math can do. That's not a problem, really. So yeah, it tells you how far off this is from that one. This, as eccentricity approaches 1 or as b approaches 0, this becomes less accurate. But you have to get pretty close to eccentricity of 1 or b of 0 for this to be very far off. This ends up having problems much sooner than that. But yeah, it's a simple little script that does that comparison for you, so you can see how accurate this is. Let me do one more. Let's do a larger eccentricity. So that part of this will be off screen, but once I enter the values, I'll put it in. So let's do a b of like 0.1. So that has an eccentricity very close to 1, but still the error is less than 1% between this and this. And out at this point, if you're using the standard 2 pi root a squared plus b squared on 2, that thing, your error is going to be like 10% or something. Yeah, it's going to be pretty bad. I don't know what it is because I haven't calculated it. I haven't looked at it, but it's not going to be anywhere close to this accurate, right? So this is pretty much never correct, but except for the circle at 2 pi, but it's always really close. And considering how simple the equation is, like this is it. This is it right here. Which, like, that can actually, if you know what b is, it's actually just, this is just 5 plus 2b plus b squared divided by 4 times pi. That's it. It's, okay, so it's, let me see if I can write it in here. Get it to be, so the perimeter is approximately equal to pi on 4 times 5 plus 2b plus b squared. And then it's going to freak out and doesn't know what that means, but there you go. Like this. If you know b, this works. This is it. This is it. That's how complicated my algorithm is. My approximation is. And it's this accurate. Like, this is at a point where, like, the accuracy is going, like, it's getting bad. And it's still not that bad. It's still under 1% error. Yeah.